high above the world as we know it, far away from what we usually see, there is a world of waters to discover. Waters that are as pure and pristine as we can imagine, strong and powerful in their ways, and waters that appear like mirrors of the sky. But high above the world as we know it, life and the waters around it also reflect the world of faraway places. Scientists come all the way up to high-altitude mountain environments because they want to keep an eye on the waters in these areas, to monitor the changes headwaters are going through. Scientists come all the way up to the remote alpine lakes above the timberline because they know about toxic chemicals that can travel thousands of miles, accumulating on the bottom of the lakes, changing the quality of our fresh water.
The alpine region in Europe has been changing since mankind, more or less, but especially in the last century there has been a huge change, especially in the chemical composition, not only of the waters but also of the sediments, and this is mainly due to an introduction of atmospheric contaminants to these alpine environments.
Scientists come all the way up here because they are looking for POPs, persistent organic pollutants. POPs are synthetic chemicals currently or once used in industrial processes or as pesticides. Or POPs are unwanted byproducts from industrial processes or combustion. POPs are persistent in nature. They can resist environmental degradation through physical and chemical processes, staying in the environment for hundreds, sometimes even thousands of years. POPs accumulate in living organisms. They don't like to dissolve in water, but they do like to accumulate in the fatty tissue of the organisms, putting them at risk of chronic poisoning. And POPs pass from one species of the food chain to the next, exposing organisms higher up the food chain to higher levels of toxicity. Eventually, it is through the food we eat, the water we drink, or even through the air we breathe, that persistent organic pollutants can enter our body. Even at low doses, POPs have been linked to cancer, damage of the immune system, endocrine disorders, Parkinson's disease, or diabetes. Scientists have come all the way from universities in Innsbruck and Barcelona. They've been monitoring changes in the chemical composition of the sediments in this alpine lake, and sediment sampling is always the first step to get new information. So a core sampler is lowered into the water until it reaches the bottom of the lake where the sediments accumulate. The higher its penetration force, the deeper the core sampler will sink into the mud, taking in different layers of sediment substance into its hollow tube. Bringing the sediment core back up to the surface is like opening up a history book. The core will not only reveal how high or low the concentration of POPs in the sediments has been in recent years, it will also uncover when POPs started to invade the waters and how much their concentration has increased or decreased over time. But why exactly do scientists expect to discover POPs in high-altitude mountain regions in the first place? How do POPs get to such remote areas of the world, far away from human activity? POPs are atmospheric contaminants. They can disperse into the atmosphere, and they can spread all over the world by atmospheric currents. POPs are semi-volatile. They can evaporate in warm regions of the world and condense and accumulate in cold regions of the world. For example, in Arctic regions. or in high-altitude mountain areas such as the Himalayas, Rocky Mountains, or the European Alps. This is where they are deposited and retained, and as the snow and the ice in these areas melts, persistent organic pollutants will find their way into our headwaters. Investigating changes in the quality of headwaters is challenging. To bring a sediment core from the bottom of the lake to the shore is one thing, but to prepare samples from the sediment core for further analysis in the laboratory is quite another. The length of the sediment core is crucial to the scientists. With a sediment core 40 centimeters long, they could reveal changes in the chemical composition of the lake sediments going back 500 years. 1.5 meters of sediments would take them back 10,000 years. But these investigations are about more recent developments. Has the concentration of POPs in the sediments of this lake increased or decreased over the past decades? Cutting layers of the sediment core brings the scientists closer to the answer. Every layer of the sediment core has a certain age, and it is the top layer of the sediment core that will allow the scientists to examine the concentration of POPs in the lake sediments as it has developed in the 21st century. Every new layer sample will allow the scientists to collect more evidence about the historical developments of this mountain lake and about any traces of humans in this region. Sediment sampling in high-altitude mountain lakes. It's a job that will never be finished.
Monitoring the persistent organic pollutants, it's very important. It's not the same sampling only once in one spot than sampling more times, different circumstances, for example, different seasons, different years, to see how is the trend.
Mountain waters are very sensitive to the changes around them. We need to look closely to uncover the changes within them, even those not visible to the eye. Far away from the remote mountain waters in the Austrian Alps, at the University of Barcelona, laboratory analysis of the lake sediment becomes the main focus of the scientific activity. How high is the concentration of POPs in the sediments, and has it changed?
So we actually came down from the mountain, from the alpine lake, with the sediment samples, and here we have them. Before we can analyze actually the persistent organic pollutants in these sediment samples, we need to go through several analytical steps. We need to get rid of the water, so we have to freeze dry it. Then we have to purify it, extract it, concentrate it, clean it up again, and finally concentrate before we can inject it into a specific instrument where we can detect the persistent organic pollutants.
The wet sediment samples that were brought down from the alpine lake have to be freeze-dried, so that the organic matter the scientists are looking for can be extracted. For each sediment layer, 1 gram of dried sample is taken for further analysis. In order to separate the organic matter in the sediment sample from the inorganic matter, organic solvents come into play. Vortexing the sample is also part of the extraction process. Throughout the process, a lot of steps are necessary in order to concentrate, purify and isolate the organic fraction of the sediment sample. It is the organic fraction that will contain persistent organic pollutants in high or in low concentrations. Once the organic fraction is collected and isolated, the scientist is close to the finishing line. What is left to do is to separate organic pollutants from the organic fraction. As the organic fraction passes through a column, impurities are filtered away, and persistent organic pollutants, amongst other chemical compounds, can be extracted. By careful evaporation, the extract is concentrated one more time. And now, the concentration of persistent organic pollutants in the sediment of the alpine lake can be analyzed. The sediment samples are analysed by a gas chromatography mass spectrometer, or GCMS for short. As the samples pass through this high-tech machine, the chemical content of the lake sediment extracts is separated. With rising temperature, the most volatile compounds will appear first on the chromatograph. This is how POPs are first detected.
So now have a look to the different sediment layers which we've been sampling in this alpine lake in Austria. We've sampled the upper layer, which is more or less the present, and we sampled other layers more below, which are representing different periods in history, in recent history. 90s, 80s, 70s, 60s, 50s, 40s. And in these different layers, we can actually analyze now the persistent organic pollutants and quantify them, so we know the concentrations in the sediment samples. So here, for example, what we see is in the sediment sample from the 60s, the concentrations of the POPs are quite high, which is also the same for the sediment sample from the 80s, while the one from the 21st century, the concentrations are much lower, which in the first sight indicates that the concentrations in the 21st century has been decreasing.
Looking closely at a remote alpine lake above the timberline can be surprising, because the concentration of persistent organic pollutants inside these waters may not be rising, it may be on the decline. What could be the reasons why the scientists are observing changes like these inside lake sediments? Nations from around the world were able to get together in Stockholm to sign a treaty to ban or restrict the production and use of those POPs they regarded most harmful. More than 10 years after the Stockholm Convention, the positive impact of the treaty can be observed today. Yet it has not always been easy to implement. Monitoring mountain environments is indispensable. It provides decision makers with information about how well we manage the health of our planet. In the case of persistent organic pollutants, the cooperation of nations, some of them separated by thousands of miles, has had a positive outcome. For mountain areas and for headwaters, the sources of our fresh water.
Mountain environments are ecosystems where many times water is generated. So water research is important to be conducted as well in high mountain areas, in general, since they are further away or farthest away from any human activity. So the water which is collected here within the rivers and also lakes is purest. So it's very important to study the quality where a river starts.
Water is a giver of life. It has been from the beginning. Water is our planet's essential resource, and always will be. Waters can be affected by human impact in many ways, today and in times to come. How well will our waters be protected? Only time will tell.